Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today we're looking at switching power supplies. And, well, this is an LT switcher. It's a boost. This is really cool. We're going to look at this another day. I've done one video on that. Today we're going to look at a low frequency switcher. Yeah, Class A amplifier, low frequency switcher. Hey, what, you don't believe me? It's a low frequency switcher? Anyway, guys, I've got an AC power supply underneath that. Just did a review on it. Check it out, okay? I'll put the link below. But what we're doing is the power's coming out, and I'm going through this little guy here. That actually creates a couple loops. So it has the line going out and the neutral going out, and I can look at the current with the current loop like this. So I'm going to show you the setup, the rest of the setup here in just a moment. But we're going to look at some waveforms. It's going to be a fairly quick video, I hope. But the power cords right here come to the Class A wrapping around here, okay? So we're looking at the current coming in. Let's take a look at that, okay? Oh, and as part of this setup, I'm using my iPad to connect to my Mixig so I can kind of talk to you and kind of talk you through what I'm looking at here. So we're looking at switching power supply, right? All those current spikes. Yeah. Now, one of the things about a switching power supply is that the average or RMS current is always a lot less than the peak currents because there's an on and off period, right? And from this, let's spread it out a little bit. You can see that the off period, it's longer than the on period. The spikes are spikes, and the off period, yeah, there we go. We're zooming in a little closer. You can see it's off, and then a spike of current, then on. We zoom in a little bit more, we can see a little bit better. Now we look at the RMS current, it's like 1.3 amps, and the peak current is 3.5 amps. Let me get a few more cycles and see if the current gets, yeah, it's staying about the same. You get more cycles, the math works out better, so you can kind of see the numbers change a little bit when I go more cycles. But it's right around 1.3 amps, 3.5 amps peak. So peak currents are, not 3 times, but 2.5 times higher, something like that. Up in the top left corner, you see 60 hertz, low frequency switcher. We got a bridge rectifier, right? The bridge rectifier makes 60 hertz and a 120 hertz. But at the input current that's going through the power cord, it's also 120 hertz because we see 60 hertz. A full cycle is 60 hertz. Now, you see a top waveform, bottom, and then you go back to the top, and once you go through a whole cycle, it's 60 hertz, right? But if we look at the spectrum of this, it's going to look like 120 hertz because we're getting spikes in the negative, spikes in the positive, and we don't care when we're looking at the spectrum. We're just looking at the spikes, and they're happening at 100, twice the frequency, at 120 hertz. Right? Okay, so you know what? Let's go ahead and look at the spectrum. I'm going to grab a couple more cycles. I'm not really positive I need all these cycles to look at the FFT. Sometimes you do in some scopes, some you don't. And I haven't really experimented on, actually for a while. I use a number of different scopes. I mostly use the Mixig and the Picoscope. The Picoscopes are awesome. The Mixig is awesome. But I used to use the GW more, and it's a great scope, but yeah, the Mixig, I think it kicks its butt, except for maybe like this Bodie. Like this guy would do Bodie plots where the Mixig doesn't have that function because it doesn't have a generator output. So yeah, the GW costs twice as much too. But anyway, just saying, I use different scopes. So sometimes I'm a little like, okay, what's this scope do compared to the other scopes? I kind of like lose track of which scope does what. But, okay, so back to the waveform. We got all those waveforms. We're going to turn on the math, and if I open it up here, you can see I have FFT is dB. Oh, guess what? And down here you see hamming. These are these window functions. So an FFT is a mathematical function that takes it takes signals for infinity, basically. It like takes all these signals, averages them, shows you this, and then goes out, averages them some more, and gives you this spike. Goes out further and gives you the next spike. So it's always going out and getting all this information and giving you the next spike, and then the next spike, and then the next spike. Okay? So when you're saying, well, I just want to look at this frequency range, it doesn't know how to stop. So basically you have to put a, stop, bookends on it. And it's also going the other direction too, mathematically. So positive or negative, it doesn't matter. Just, it does that thing. All right. So these window functions, it's like a window. Hey, there's all this stuff going by. The train's going by. There's front of the train over there. There's the back of the train over there. But in this window, we just see these 3 or 4 cars going by. And, so there's different ones because they behave differently. And so Hamming, rectangle, all that. Anyway, window function. We got it on Hamming. Persistence. I just did a short video. They just added persistence to the firmware. So that's awesome. Now, I mean, they had persistence before for the time domain, but now they have it for the frequency domain, the FFT. So that, way to go, McSig. Awesome. That's something you don't see in too many scopes, right? I'm trying to think of any scope I've seen that in the FFT. All right, so our math is on. Now, you know what? Let's go back to channel 3 and turn that, or 4. And let's turn that off. I find that's one thing about the app. Maybe I'm doing something wrong, but when I try to swipe it and turn it off, it doesn't turn off. Okay, so here's FFT. It's actually, I've got it spread out already. And look, on the third waveform over is the first spike. And that little red date up at the top of the screen, top corner, left corner, it says 60 hertz, and it says DC is minus 43 dB, and it says amplitude is minus 2. So, these are 8-bit scopes, right? So that you can't get really deep depth like 100 dB. I mean, the noise floor on this looks like it's, what, like 60 dB? 80 dB is trying to get down to 80. So, but if you look really close, here, I'm going to try to spread it out a little bit more. Okay, I'm spreading it out. See those? Okay, I'll put the 0 dB right at the top of the screen. Okay, so 0 dBs is the top grid of the screen. So you see the first waveform, that's 60 hertz. Then the next one over, if you look down in the noise floor, you see those little spikes. You see little spikes in between the big tall ones. Those are every 60 hertz. So that's the 60 hertz harmonics, okay? But the big ones, because the bridge rectifier in the Class A amplifier, and pretty much I would say most low frequency switching power supplies use a bridge. Some people call them full bridges, but a bridge is, the full bridge. Anyway, a bridge has 4 diodes, so you get all waveforms. If you do a half wave rectifier, you use 2 diodes. But, most often there are 4 diodes, right? So, okay, so 120 hertz. And that is the frequency, the dominant frequency. Let me turn on my bars. And I'll put this bar on that spike, pretty close at least. Okay, that's at 180 hertz, it says. And I'll grab this other one, move it to the next tall one. And that's at about almost 300 hertz, it says, 301. If I moved it over, yeah, there we go, 300 hertz. So 120 hertz. The delta X is 120 hertz between the two major, the high spikes. So all those high spikes are 120 hertz away from each other, because that's actually the power frequency coming in. It's 60 hertz line. That's plus to the next plus cycle. But we're using plus and minus cycles in a bridge rectifier to create, a charge on a capacitor, right? So it's really 120 hertz. It's twice as fast. So that's what you're saying there is 120 hertz. And look at all those spikes though. So here, let's get some more of them in here. I'm going to hit the thing. Let's move them over. Yeah, look at all those spikes. Okay. Now, I'm out to about 6 kilohertz over to the right, if you look at the bottom of the screen. So, but look at that. I mean, all through, through the majority of the audio range, you have some pretty decent spikes in there. So hopefully the second stage of the power supply will take care of that. Now here, you know what? Before we talk about that, let me show you the setup here, okay? Let's just jump to the setup. All right, guys, let me show you the setup, okay? So we come over here, and on the screen here, we have 1.29 amps and 3.6 peak. We have 1 amp by division, so it's 1, 2, 3.5 up, which is what that's saying. RMS 1.29. And we're using the RCP 500, which is good for 500 amps. So that, resolution could be a little bit tougher down here at the low currents. 15 hertz to 300 kilohertz, so we're good for frequency. But let's come over here and see what this guy says. All right, so this guy is actually saying we're 1.2 amps and 120. So it's pretty close to what the scope is saying. So it's pretty close to the scope. It's saying 1.29, and we're at 1.2 right now. So they're pretty close in agreement. Now here, let me show you the rest of the probe. Here's the MIG-SIG probe, and it's looped on this guy here. Let me bring you over to the front of it. So this is a redfish one, but it's ×1 here. So whatever we're reading is 1 to 1. And over here is ×10. So I could put it on here because it would have made it look like 10 times more current. Maybe we'd have got a better resolution accuracy. Maybe we'd be dead on. But just for fun, let's bring over the Hioki, okay? Guy's meant for solar stuff. It does all kind. It does AC, DC. It's good for everything. But it is good for up to 1,000 amps. So let's see what resolution we get out of this. Okay, 1.1. So it's pretty close. Pretty close. Here, let's try the KPS. Another meter meant for a lot of current, up to 600 amps. So let's see its accuracy down here at the lower currents. One thing, when I open up JAWS, it turns on a flashlight so I can see where to put it in. That's pretty cool. Automatically does that. So it's 1.21. The same as our IT Tech display. So these guys are pretty much rock on. So yeah, we like it. Okay. So it's nice to have a little backup measurement there. But like I said, if we've gone to ×10, we just divide our measurements down by 10. And we probably get a little better accuracy because, right, looking at 1 amp on devices that are good for 500 or 600 amps. Yeah, we're asking a lot, but they're actually doing well. All right, guys, so you saw the setup, okay? So, you kind of probably really guessed it, but yeah, this little MIG-SIG current probe, pretty cool. It just has this little magnet thing that goes pop in there, and I just take it around, and these things are really handy to go on a panel or whatever to measure current, so really handy. And for a low frequency switcher, they're working great, right? Even though this thing's designed to look at high currents, it's done pretty good down here at the lower current range. Okay, guys, so in a power supply, like in a Class A amplifier, the low frequency switcher, which is nice and toasty warm, that's why I'm leaning on it, because my lab is 12 degrees C, and the Class A is a toaster oven. So I'm actually able to kind of lean on this bad boy. We're pulling around 100 watts, and we're not doing anything. It's just no signal going in. So there you go. And it's about a 60 watt amplifier with 30 watts per side. So 60 watts total, both sides. And right now 100 watts, no signal. So you can see how inefficient a Class A amp is. But at 100 watts, we're seeing some pretty decent spikes. And some. All right, so guys, in a low frequency switching power supply, a little bit different than a high frequency switching power supply. You know, in a low frequency switching power supply, you're going to take this 60 hertz signal, you're going to convert to 120 hertz, and charge up some bulk capacitors. And then, well, we're talking audio, right? And other power supplies, then you would regulate that DC power. And then that regulation would be linearly regulated. So that's where mistake comes in. People just offhandedly call all low frequency switchers linear regulated power supplies, where when it comes to, say, audio amplifiers, they often kind of cheat because they don't regulate them. They've sold the audiophiles, the audio people, into even thinking that's a good idea, where that's ridiculous. But you know, even the guys working in the industry think that that's true because they're audio engineers. Sorry, didn't mean to take a stab at you, but you're not power supply engineers, right? There's probably some of them out there, but for the most part, the guys design the audio amplification circuit. They're doing the power supply circuit because the companies just don't have enough money to pay for a power supply guy like me to come in and do power supplies. And then they don't understand power supplies enough to understand what I'm doing for them or the benefit. I mean, there are a few of them out there, and they're going to be, you know, the predominant thing. Anyway, that's for another rant. I've done one rant on that subject before, but I got another one because somebody said something, and anyway, let's move on. So in an audio world, they just take the low frequency switcher, bulk up the capacitors, and just use that raw voltage, and they think that's a good thing. They think that that's a faster thing, like linear regulators are slower. That's wrong. That's absurd. It's funny how many, I've even seen some smart people say that, and it's, wow, they're just like so far down the wrong road, they don't even know where they're headed. So on one aerospace program I worked on, I had to show, because I told these guys, hey, we're going to get rid of that big old capacitor, and because we can't use it anyway for aerospace, it's not allowed, so, but we don't need it. And they're like, well, okay, can you prove that to us? I'm like, yeah. It always takes, you know, the first guy that came along didn't know really what he was doing, no time at all to convince everybody that that's a good thing. And then the guy that comes along that knows what he's doing, it takes him, you know, twice, if not 10 times as much work to explain or reconvince people that that original idea was a bad idea. So that was one of those kind of deals. And, you know, so I could go to a lot smaller capacitor instead of the big capacitor because I was using the regulated output. And a regulated output is a regulated output. It holds the voltage flat. Yeah, there could be some dips and stuff, but the regulation circuit will do everything it can to keep that capacitor and keep that voltage level, right? In an unregulated power supply, big old bulk capacitor, that thing will dip all over the place. You need more, bigger capacitors to try to hold it level, and that's what's happening in the audio world. Oh man, the bigger capacitors you can get, the more of them and the bigger of them, oh, that's the way to go. Well, that's because they're chasing their tail, and they don't really know how to design power supplies. So, and also they don't want to pay for them. And the power supply, an audio amplifier essentially is a power supply. So they'd basically essentially they'd be designing something twice the size of what they have to regulate the outputs. So that's the real reason. And then they fool everybody by all this stuff. So that's why I think it's important to understand that these are all switching power supplies. These are low frequency switchers. We've seen the switching, right? The diodes are commutating. They're turning on and off, causing these spike currents. You don't get current in a sinusoidal fashion like the voltage coming in. The voltage comes in sinusoidal, but the current is pulsing, switching on and off. So The second stage of a power supply is where the terminology of that power supply has come from. As far as linear, as far as big power supplies, they'll just call this a linear power supply when it's not. There's nothing linear about it. Now, if you regulated it in a linear fashion, then it'd be a linearly regulated power supply. The front end would be a low frequency switcher feeding the linear regulated output. And that'd be the proper terminology for the power supply. And I think the reason it never really got pushed that way from the early days and everybody just kind of went with it was because when switching power supplies came along, I think it was the aerospace engineers, people doing space and aerospace that drove that. And then it went into commercial worlds and everything. People thought, wow, switching power supplies are awesome. But the people that had the research money and all that were, like I said, the defense contractors, the military people. That's my guess. I think if we did some research, we would find that's true. But the power supplies they were replacing back in those days were lower power things in aircraft and so on for the flight controls, all these things, and everything is regulated. And so they're like, oh, now we're getting rid of those linear regulators and we're going to switching regulators. And then people just started cutting it short saying linear power supplies, switching power supplies, which I'm trying to change that because it's not a good way to look at a circuit, because you have to understand that the front end of this is switching on and off. Therefore, you can design the parts correctly and you know what you're dealing with, and you know that you have FFT stuff. You can, on the FFT, you can see all those harmonics. In a linear power supply, why would you have any harmonics? So there's no such thing as a linear power supply. If it's coming from DC going to DC, then it's linear regulated, right? I mean, then you could say a linear regulated power supply is a linear power supply. You could throw off the regulated part of it and just call it linear power supply. Anyway, so kind of on my, maybe I should call this a rant video, but I wanted to show you guys what the switcher looked like, okay? So, yeah, hope you liked it. Thanks for watching. 2 big thumbs up, my patrons. Appreciate you guys as always. 2 big thumbs up, my members of my channel. I think I still have 5, and one of them's a team member. Thanks so much. And let's see. Oh, I had someone hit the super thank you button. You can buy me a cup of coffee or buy me a beer for a rant, and that's right down below where you hit the thumbs up. Thumbs up is, hitting the thumbs up button's a free way to support the channel. Using the links down below to buy all the stuff that I've linked up down there. That's a free way to support the channel. And yeah, you can become a patron. That link's down there. It was as little as $1 a month. And you become a member of the channel. There's a member right down there by that super thank you. So thanks guys. Thanks for watching. Hope this was helpful, useful, and that you could see that just because you have big toroid, big capacitors, big everything, big transformer, there's nothing linear about that. You can see there's no linear waveforms. It's a low frequency switcher. After that, it should be regulated. And then you could say it's a low frequency switcher. Second stage is linear regulation. Now, today, if you're still with me, today what we do is we do active power factor correction. So now the first stage, instead of a bridge rectifier, instead of that just being a simple bridge rectifier, now it's a PFC stage. So we try to keep that current in a bunch of little smaller pulses, lots of them, so that it's easy to average with the capacitor to make it look like a sine wave. And then we can line up the current and the voltage and keep the power factor near 1. So the VA and the watts going in are essentially the same thing. You don't need, say, 130 VA to give 100 watts. Okay? You don't have to have that extra overhead on your power system. You're actually using what you're asking for. So the first stage is that. Second stage is a switching power supply with isolation, like the big transformer in this, and then regulated outputs. So it's a switching, isolated, regulated output. Okay? So it's a regulated switching power supply with isolation. That's probably proper way to call that. And yeah, so there you go. Thanks for watching. See you next time.